Okay, in this video I'm going to go over how to draw free body diagrams for objects that are experiencing relatively simple one-dimensional motion. A free body diagram is a diagram that shows the forces, the direction, and the relative magnitude of the forces that are acting on an object. Okay, so here's the very first one, the book. It's at rest on a tabletop. It's just sitting there. And I like to ask myself, just to be sure, does that mean that the forces are going to be balanced or unbalanced? Well, the book is at rest as a constant velocity, which is zero. It's not moving, so its velocity is constant, but it's zero. And that means the forces are balanced. And therefore, when I draw it, it has to look balanced. Balanced forces, well, let's just say constant velocity means the forces are balanced. The net force is zero. Okay, so the first force we're going to draw is the force of gravity downwards. And then it's sitting there on the tabletop, so the tabletop must be pushing back up on it. It's the force applied by that surface onto the book. We call that the normal force. It acts normal, perpendicular to the surface between the book and the tabletop, which is this surface right here. And it's opposite and equal to the gravitational force. And we would just draw that one, and we draw it just like that. Okay, the book is at rest. Okay, the next one, you have a rightward force that's applied to the book, and it's moving across a rough desk, a rough surface. We're going to include friction, and it's speeding up. Its velocity is increasing, so that means it's accelerating, and that means the forces have to be balanced. In order for it to be accelerating, the forces have to be balanced. And if it's speeding up, then it's accelerating. With increasing velocity, then it's accelerating, and the forces are unbalanced. Excuse me, did I say balanced? Unbalanced. And we're going to draw the gravitational force. We're going to draw the normal force again. It's not falling through the tabletop. And there's a rightward force that's applied to it, so we're going to call that our applied force. And then it's a rough surface, so we have friction, but now we got to figure out how long are we going to draw and in which direction are we going to draw the friction vector, okay, for the friction force. And that means that it's going to be opposite the applied force because the friction opposes motion, so it points in the opposite direction to the way the object is moving. And because it's increasing its velocity, the friction force has to be less than the applied force. Okay, the force that you're pulling it with is greater than the friction force. And we can see that the friction force points in that direction and opposite, and therefore we draw it like that. Okay, so that's how we draw that for that one. And now we're going to go on to the next one. Now you're pushing the desk to the right, across, and it's moving at a constant velocity. It's just you're pushing it, but it's pushing back, so to speak, and you're moving with a constant velocity. We draw the gravitational force downwards, we draw the normal force upwards, and then we draw the rightward force for the applied force. Now, what is keeping it from speeding up, or what is keeping it from accelerating in this case, because it's moving to the right? It's going to be the friction force, and you'll notice we draw it equal and opposite of the applied force. Those are balanced. That means that the object is moving at a constant velocity. Okay? Now, it could be standing still at this case, but in this case, we already said it's moving to the right, and it's moving right across that surface. All right? Now, we're going to come to the next one. The book is sliding to the right across the rough tabletop and coming to a stop. Now, it doesn't say anything about an applied force, so there is no applied force. It's coming to a stop. That means it's accelerating, it's slowing down, and the forces are unbalanced, and therefore we draw the gravitational force downwards, the normal force upwards. There's no applied force, but what's the force that's causing it to come to a stop? That's right, that's friction, so we draw friction opposing the direction of motion, and therefore we label the friction force like that. Okay, now a lot of people will think, once again, that because we have a force to the left, there has to be some other force to the right, but it is not. There is no force pointing to the right. There's no applied force. Don't draw a force unless it says that there is a force. Okay? All right. The next one. Now the book has just come back to a rest, and it's at rest on the tabletop, constant velocity, and we're just going to draw it. This looks just like the very first one. Okay, so basically for those last slides, we took the book from standing still, accelerating, constant velocity, and then slowing down. Okay, so now we're going to do some different ones, and let's see what we have here next. Now we have leftward force is applied to a box to move it across a frictionless surface, and the box is accelerating. If it's accelerating, the forces are unbalanced. It's a leftward, and it does say it's a frictionless surface. So once again, gravity first, normal force second. And it says a leftward force, and all we have is an applied force, and we don't have any friction, so it looks like that. Once again, people think, okay, there's a force to the left, there has to be a force to the right. There does not have to be a force to the right. It's just like that. Okay? And the next one, this is a hockey puck. It's sliding across a frictional surface, and it's moving at a constant velocity. The constant velocity is means that the forces are balanced. Now it does say here the hockey puck is sliding and I have equals 0. That's not true. The hockey puck should be, the velocity is greater than 0, but still the velocity is constant and therefore the forces are balanced. We draw the gravitational force downwards. We draw the normal force from the surface of the ice upwards, and that is all that you would draw. Okay, a lot of people think, okay, it's moving, there has to be some force pushing it, but there does not. According to Newton's first law of motion, objects in motion stay in motion, objects at rest stay at rest unless acted upon by an unbalanced force. Now, some force had to get it going, but once it's going, you don't need any force to keep it going. It will go on and on and on forever. All right, now on Earth, that usually doesn't happen because we have friction, but you can think about it if you've ever been ice skating. You hit a hockey puck, give it a nice slap, it'll usually go pretty far without slowing down or stopping. Okay, so that's all there is. That's the same one for an object at rest. That has constant forces, constant velocity, and balanced forces. So does this one. Okay, next, a girl is suspended motionless from a bar. It's hanging by ropes, constant velocity. Her velocity equals 0. The forces are balanced. There she hangs downwards. Here is the object, which is she, hanging. There's the gravitational force. Now it says she's suspended by 2 ropes. So we're going to draw the 2 ropes pointing upwards. And both of those are from the tension force. And those are point upwards. And they're in the opposite direction. Okay? All right. Next one. And an egg is free falling with an increasing velocity. We want to include air resistance. So there's our egg. It's accelerating. It's increasing its velocity downwards. Has an unbalanced force with the force of gravity. It does say to include air resistance. Now, how big are we going to make air resistance? We want it to be increasing its velocity. So the question is, the air resistance going to be the same as the gravity force, less or more? And if it's increasing its velocity, the air resistance has to be less. Okay, so you can see the way that I drew this is the force of gravity is greater than the force of the air, and that means that it's speeding up. All right, now we have an elevator that's moving downward and slowing down. So it's accelerating, the forces are unbalanced, we draw the gravitational force, now it's moving downward and slowing down. So the question is, we have to have some force pulling upwards, and if something is falling down and slowing down, how big is that force going to be? Well, the force has to be greater than the force of gravity. Okay, if you want it to slow down, you got to pull harder than gravity, and therefore we have what we could call the tension force, the force from a cable or a rope or something like that, and then we draw it like that. There's no forces to the side. Okay, I think we're getting close to the end here. Here's an elevator that's moving up and speeding up. So it is speeding up. We have acceleration. It's accelerating. It has unbalanced forces. We draw the gravitational force downward. It's moving up and speeding up. Well, if you have something that's hanging in your hand and you want to accelerate it upwards, how far or how hard do you have to pull? Well, you have to pull harder than gravity. Okay, so once again, we're going to have it on a tension force. An elevator is usually hung by a cable, and therefore we have the tension force that way. And that would be, you're pulling it upwards, you're overcoming gravity, you're pulling harder than gravity, and therefore it's going to be speeding up. Okay, now you'll notice, maybe if you remember, that this slide and the previous slide, the drawings were exactly the same. And that's right, if something is moving downwards and slowing down, it would look like this also, moving up and speeding up. All right, so let's see. Thank you very much for watching. I hope that was helpful. If you thought that was helpful, then you can leave me a comment or a thumbs up in the comment section below, and we will see you next time. Thank you.